All right, well, welcome back everybody, and what we want to do in this video is take a look at the carbon-carbon double bond containing functional groups, the alkenes. And so we'll take a look a little bit at their structure and their bonding, and we'll kind of look at a bit their stability. And this will be a lead in to first to the aromatic molecules, which we'll talk about after this, and then ultimately a lead into the section on functional groups, where we start looking at more and more complex arrangements of atoms. So first we want to start by taking a look at the simplest alkene, ethene. So we'll just draw it out here on our whiteboard. So each of these carbons has two hydrogen atoms attached, and then we're drawing in the carbon-carbon double bond. And so we've likely seen a little bit of this already, so I won't go too depth into this here. But what we observe about this particular molecule, again, these are observations, it's trigonal planar. And 120 degree bond angle. So the molecule, the whole molecule, this ethene itself is planar. Each of those carbon atoms is at a 120 degree bond angle between the other carbon, the other two hydrogen atoms, and the whole thing's planar. And so the best sort of model that we come up with for this is we describe it as an Sp2 hybrid. So we developed this Sp2 hybrid model. Again, this is the explanation that we have for the observations that we make about these atoms and the way they form these bonds. So what does that explanation really mean? Well, if we look, for example, how we build up the model of this Sp2 hybrid, we come to something like this, where our explanation says that, look, we've got, in order to be able to make two bonds between each of the two carbon atoms that are involved in this, our explanation is that each of the carbon atoms must unhybridize an atomic p orbital, and that atomic p orbital sits up and we get this side-on overlap of that p orbital. And in fact, this is what we refer to as a pi bond, as compared to the sigma bond, where we have the direct overlap of the orbitals that are involved in the bond. Now we've got these two unhybridized atomic p orbitals. Again, just another representation of this on the screen. These unhybridized atomic p orbitals that are kind of sitting there side by side, each with a single electron in them. And we say, look, those kind of interact in some way that allows them to share those two electrons. And so this is, in fact, often the model that we refer to as the valence bond model of these unhybridized atomic p orbitals, kind of side-on overlap. And often we use this model as a way to describe some of the behavior that we observe. And occasionally we'll use this particular aspect of the model of bonding in this molecule to just as a shorthand to sort of understand what's going on, especially, for example, when we talk about eliminations a little bit later. But this particular model is not entirely satisfying either. I don't think it explains everything about why we expect to observe a bond here. And so the other model that we develop is this model here, where we kind of develop the molecular orbital model, where we say instead of just a side-on overlap, we can treat those unhybridized atomic p orbitals like we can any other atomic orbital, and we can mix them together in both a constructive and destructive manner. So this and form a new orbitals that are more consistent with the molecule. And so this is one of our explanations. We take each of those two unhybridized atomic p orbitals, we mix them together mathematically, and we generate a set of two new orbitals. One where we get constructive overlap between those atomic p orbitals, and the other where we get destructive interference or destructive overlap between those atomic p orbitals. And our explanation is that, look, if we get that constructive interference between the two atomic p orbitals, they wind up lowering the energy of the entire system. And so if you look at this at the depiction of the molecular orbital here, what we're showing, the red and the blue, really is just showing the electron density, or the probability of finding the electron density in that region. And the highest probability of finding the electrons in this case is between the two atomic nuclei. And so having electrons shared between two atomic nuclei, that's our very definition of a covalent bond. And so having those electrons go into that bonding molecular orbital, as we call it, that bonding molecular orbital lowers the energy of the entire system. So that's our explanation for why that bond really is stable and likes to exist. Now, the other orbital that we can generate as part of this mixing process must be higher in an equal and opposite amount than the two isolated atomic p orbitals. We can neither create nor destroy energy, so that other orbital goes higher in an amount, that destructive interference where they don't interfere with each other, where they cancel each other out. And if you look at the shape of that orbital, the electron density, the red and the blue colors, suggest that our highest probability of finding the electrons is anywhere but between the two atomic nuclei. So that's exactly the opposite of our definition of a covalent bond. We call this the anti-bonding orbital. And putting electron density into an anti-bonding molecular orbital will destabilize that chemical bond. We don't see much of it here, but we'll talk about this a little bit later when we talk about things like substitution reactions and why those proceed in the way that they do. So here, this molecular orbital picture of bonding in these alkene bonds is our explanation for why we can see this second carbon-carbon bond as being stable in these molecules. So what we want to take a look at now is a measure of the stability of these double bonds. Do we have a way of measuring the energy that's contained in them? Because we'll see as this leads into our continuing our discussion about structure and reactivity of these particular molecules. So we do have a reaction that we like to use for measuring specifically the energy that's contained in these double bonds. And so I'll just draw out the reaction here. So there's the reaction. We take a molecule of ethene or ethylene, any kind of double bond containing molecule. We take a molecule of hydrogen gas, and we take a catalyst of some kind, in this case platinum. You can also use palladium, and there's a couple of other transition metals in general that you can use to catalyze this reaction, but platinum is the one that's most commonly used. And if you follow the balanced equation here, you can see that the two molecules, or two atoms of hydrogen from the molecule of hydrogen gas, get added to the double bond and wind up removing the double bond itself. So it's a way of taking a look at the energy in that double bond itself. So this reaction is actually called hydrogenation. Hydrogenation, and we can use the energy that's given off by this chemical reaction as a measure of the heat that's in those, or the energy that's retained in those bonds. So delta H naught with a little subsymbol H, and that's to distinguish this from the combustion, from the heat of combustion that we talked about right at the very start. So here we're not combusting the whole molecule, we're looking explicitly at just the double bond reaction. So the heat of hydrogenation, or the enthalpy of hydrogenation, is what we're looking at here. And so specifically, what's the heat of hydrogenation for this particular reaction? (137.2 kilojoules per mole). So 137.2 kilojoules per mole is what's being released when we carry out this particular reaction. Now, of course, this fact on its own doesn't really tell us much of anything, so what we want to be able to do is look at a table of these heats of hydrogenations to be able to get a feel for what happens as we start making changes to the structure of our molecule. So let's take a look at that. Here's a table of some of these hydrogenation values. So again, we're carrying out this hydrogenation reaction on a series of alkenes where we're putting more and more substituents on each of those alkenes. And what you observe is that the energy that's contained in that double bond is, we're looking here as we go, for example, from ethene at 137.2, then we put another substituent on there, so immediately below that entry in the table, it's 125.9 kilojoules per mole that's released in that reaction, 115 kilojoules per mole in the next entry below that, where we've got now 4 carbon atoms in total. We put another substituent on the double bond, it goes down to 112, and then down even a little bit more, down as we add yet a 4th substituent on there. And so we've got these trends that we've observed here. So our observation here from this data is that the heat of hydrogenation is decreasing as we add more methyl groups. And again, this is a measure directly of what's contained in that double bond. So the energy contained in that double bond seems to be less and less as we add more methyl groups. So the conclusion that we can make from this set of data is that more substituted double bonds are more stable, because we're using energy as a measure of the relative stability of a molecule. And here, if we're looking directly at the stability of that, or the energy in that double bond, it's another measure of the stability. So the more and more substituents, the more and more stable that double bond is. Okay, so what's our explanation for this? Our explanation is something that we call hyperconjugation, which is the donation of electron density into from the methyl groups into the molecular orbital itself, and specifically the molecular orbital of that pi bond itself. And so again, there's that representation of that pi bond. We'll see if we can draw, if I can draw something out to get, at least in a cartoon, that gives you a bit of an idea of what might be happening here. So again, if I imagine that carbon-carbon sigma bond, that direct overlap of the two sp2 orbitals kind of holding those two carbon atoms together, and I've got something like a methyl group here, CH3, so I've got those methyl groups sitting there, and then I imagine that molecular orbital. The molecular orbital sitting above and below that sigma bond sitting there, that sharing, that mixing of those two unhybridized atomic p orbitals, generating this new molecular orbital, 2 electrons in there. And we said, look, our very definition of a bonding molecular orbital is an orbital where adding electron density, adding electrons electron density stabilizes the molecule as a whole. So where do we get electron density from to make this double bond more stable? That comes from these methyl groups here. Right, there's 4 of those methyl groups, although we see the same effect even with just adding a single methyl group on it. The heat of hydrogenation from just adding a single methyl group is quite considerably lower than no methyl group at all. And again, if we think about what those methyl groups really represent, our model of what those methyl groups are 6 electrons, each pair involved in holding a hydrogen atom onto that carbon of those methyl groups. So we've got this cloud of electron density kind of just existing there in those methyl groups next to this bonding molecular orbital of the double bond. So we can imagine that those clouds of electrons, again, these probability densities of electrons kind of being anywhere, can interact a little bit with those bonding molecular orbitals of the pi bond. So we get a little bit of an interaction there, and that is we can imagine those methyl groups donating some of their electron density into that bonding molecular orbital. Having electron density in a bonding molecular orbital lowers the energy of the overall system and kind of makes it a more favorable, lowers the energy of it. So this is our explanation again for the observation that we make, is that this phenomenon, we call it hyperconjugation. So hyperconjugation is this phenomenon where you're adding electron density to bonding molecular orbitals. And so we'll see this again in a couple of other instances, in particular when we talk about carbocation stability as well too. So this is a phenomenon we'll use to explain what we observe from time to time again. Okay, and so that's the explanation again for this table of stability of double bonds that we observe here. That whole table is explained by that. Again, the more and more substituents we put on there, the more stable each individual double bond is. Okay, so what I want to take a minute to look at here, just as a way to kind of wrap this up, is what the influence of adding a second double bond is to these molecules. So introduce the concept of dienes. Functional groups with more than one double bond. Well, let's take a look at the structure of some of these, and in particular, we're going to focus on the heat of hydrogenation of some of these molecules and see what trends we can potentially observe there. So there's a molecule with one double bond in it, a couple of extra carbon atoms, and our heat of hydrogenation for this molecule. Heat of hydrogenation is 126 kilojoules per mole for that particular molecule. Now I'll take another look at a molecule with two double bonds in it. We've got two double bonds in this particular molecule, 5 carbons long. There's a carbon in the center that's sp3 hybridized, 254 kilojoules per mole. And so far so good. This makes some sense. We've got one double bond in the very first molecule, and adding a second double bond, it basically doubles the heat of hydrogenation. The total amount of energy that we get out, or the energy per double bond, is roughly the same. Now, if we take a look at this isomer of that second molecule, so we take a look at the isomer of this molecule where we've drawn the double bonds. So we've got double bond one there, and those adjacent carbon atoms. Those adjacent carbon atoms, we've got a double bond of those adjacent carbon atoms. What we observe is the heat of hydrogenation is only 226 kilojoules per mole. Right? That's a difference . That's a difference of 26 kilojoules per, 28 kilojoules per mole difference there. Okay, 28 kilojoules per mole. So look at what we're observing here. We go from one double bond to two double bonds in the first system. We roughly double the heat of hydrogenation that we observe. But if we move those double bonds where they're adjacent to each other, that is, they're no longer isolated from each other by an sp3 hybridized carbon, then what we observe is the total heat of hydrogenation goes down by an amount of 28 kilojoules per mole, or roughly 14 kilojoules per double bond, if you want to think of it that way. So of course the other way to think about these energies is that, our observation is the heat of hydrogenation. Our conclusion is that these double bonds that are adjacent to each other are somehow more stable or lower in energy than the ones that are isolated. And so let me draw this out here again just to make sure I can convince you. Here's what I mean by isolated double bond. If I take a look at this double bond here, that's the first molecule that I drew. That's the first molecule I drew, and the two double bonds, the two pi bonds, are completely isolated from each other by that sp3 hybridized carbon. They can't interact with each other in any way at all. And so they act just like they're two independent double bonds, and we observe that in the heat of hydrogenation. And the other molecule that I drew these double bonds are now next to each other. they're next to each other, they're what we call conjugated. Conjugated double bonds. They're double bonds that are only separated by a single bond. Conjugated double bonds are separated only by a single bond. Unlike these double bonds in the first isolated system, I can draw that in here, these are isolated. They're separated by more than one single bond. In this case, it's two, but in some cases it can be more than that. So they're isolated and independent of each other. Here, these are conjugated. And if we think about what this really means, it really means that the orbitals that are forming each of these pi bonds, right, we have an unhybridized atomic p orbital on each one of these carbon atoms. I can draw them in here in a way that kind of, and I'll show you a figure out of the textbook in a second. Those atomic p orbitals that are forming those double bonds are all adjacent to each other. They're conjugated with, they're adjacent to each other. That means they can interact with each other. And so if we were talking about our original model for the carbon-carbon double bond, where two isolated atomic p orbitals were interacting with each other to form a new molecular orbital, what we really have here now is 4 atomic p orbitals that can interact with each other to form a new complete set of molecular orbitals. And so we can maybe come up with a diagram for what this might look like here, and maybe a little bit better than what I've drawn here. Is that, again, this is a figure taken out of our textbook, is that if we've got those 4 unhybridized atomic p orbitals, they can all interact with each other, and they can all come together in a constructive interference way and form one strongly bonding molecular orbital that stabilizes the whole system, plus another bonding molecular orbital, which we're showing on the second one up above, slightly higher in energy, but it's still the same. And what we're seeing here is all 4, for example, of those atomic p orbitals mixing together where they're all in phase, they're all reinforcing each other, or they come together where 2 are reinforcing each other, 2 are reinforcing each other, but they're out of phase with respect to each other, so a node is what we call that in there, is still lower in energy than having isolated atomic p orbitals, so stabilizes the whole system. We've now got 2 bonding molecular orbitals stabilizing the whole system. And then, because we can neither create nor destroy energy, we also have to have then 2 anti-bonding molecular orbitals that are higher in energy from those atomic p orbitals by an equal and opposite amount as our bonding molecular orbitals are. So we observe those, we can calculate those or make diagrams that explain those. Again, these are all effectively out of phase interactions. We're putting electron density in there, would destabilize the whole system. So why are those double bonds, when they get closer together, lower in energy individually? Because we can put more electrons in bonding molecular orbitals. We've got 4 electrons for each one of those isolated atomic p orbitals, or 2 electrons per each of those pi bonds, and putting all that electron density into those bonding molecular orbitals stabilizes the whole system in a way that those isolated double bonds can't. And so in general, this is what we observe with these conjugated double bond systems, that the more conjugation, the more interaction you can get, the more molecular orbitals you can make, and they overall stabilize the entire system as well. And so the next video that we'll be posting up in this series, I think Dr. Davis will be taking over for me and kind of introducing you to aromatic molecules and telling you about some of the molecules that can make up aromatic systems.